Hello fellas, how you doing? I'm engineer Leonardo from Brazil, a civil engineer. uh, well, now I'm planning to begin after the series of videos on Navier-Stokes. I'll change a little bit the focus of the channel and start doing a series of videos on CFD and other topics such as solid mechanics and whatever you may suggest. So I'm looking forward for suggestions on this video for new topics to talk about concerning engineering and physics and mathematics. Okay, so for now I'm going to start this series on CFD, on Computational Fluid Dynamics. And on this video, I'd like to talk about what exactly is fluid dynamics, computational fluid dynamics, and or simply CFD, and what is the principles behind it and motivations, and how can this knowledge and this field aid our engineering projects and engineering designs, and besides that, our understanding of the role and the physics underlying flows, right? So essentially, computational fluid dynamics (CFD) is part of a major field which is applied mathematics and numerical modeling of the physical world which surrounds us, right? Us as humans, we are always trying to model certain phenomena, certain mechanisms and uh, happenings of our reality. We are trying to understand reality, and whether you're mathematician, a physicist, or engineering, we our biggest goal is to model and understand nature in its in its full in its full let's say mechanism, right? Understand nature in its completeness. Okay, so there are various levels of abstraction in which we can model nature. On the more fundamental level, we have quantum physics, which aims to model and describe with great accuracy, and it has obtained great results concerning accuracy of and made great predictions of the physical world through its theoretical derivations, right? So we use these models in physics, in applied mathematics, and in engineering, or there are varying levels of complexity to these models, right? So in engineering, for practical let's say for everyday practice of engineering design and project and planning, we tend to use the most simplified models and most reliable models for the problem we are modeling, right? So, well, we have these models, and usually they are fundamentally mathematical models, right? So they are based in mathematics law, and mainly in conservation's law. We have conservation of mass, conservation of energy, conservation of momentum, and many other uh, conservation laws, right? So we always tend to simplify these models for our particular problem, right? So keep that in mind, that you don't have to use an complex, an overly complex or too complex model. You always use the most complex model to solve your engineering or physics problem, right? If you can simplify your model to a more simple one and made some assumptions that will uh, make your solution to your problem more faster and easier to implement, use them, but use with care. So you must be very aware of the limitations of your model, the assumptions that are behind the model, right? So you must understand how your mathematical physical model is derived, where it came from, what are the mathematics behind it. So keeping that in mind, we have in fluid in the field of fluid mechanics, we have many theoretical derivations. So let's say we use a very complex model to simulate a flow. We can always use a more simple theoretical results to validate our result and our study, so we know we are in the right way. Okay, so back to the main topic. What is CFD, Computational Fluid Dynamics? Well, Computational Fluid Dynamics concerns the field which we take these governing equations of fluid flow, which are essentially conservation equations, like conservation, as I said before, conservation of mass, conservation of energy, and conservation of momentum, among others. We take them and we don't use an analytical approach. Our analytical approach will serve as a validation method and a method of control of solution if we are in the right path to our engineering or physical problem, right? So we take these equations and solve them numerically, but using a computer in this case, right? We can solve them, use a computer because a computer is fast doing these computations with numbers. It's fast dealing with numbers, obviously. No human mind can compete with the computational speed of calculations, mathematical calculations, algebraic calculations of a computer. So we take these mathematical equations, these mathematical models, and we transform them into algebraic systems of algebraic equations where a computer can understand. So computational fluid dynamics, we are concerning fluid flow, obviously, then is essentially taking these conservation equations, which are usually written in the form of partial differential equations, which describes a flow in each point are the partial differential equations, PDEs, are the most powerful tool in describing with very good precision and emulating a physical phenomenon. So we take these equations and transform them into algebraic equations so a computer can understand. But remember, these algebraic equations are not the same as the original conservation equations. There will be only an approximation. It could be a good or a bad one, depending on your modeling, depending on how good is your approximation method, your mesh, and other factors that I will discuss later on. So it will never be an exact solution of your flow, your model. So we have these conservation equations, and now we have discretized them, we have transformed them into algebraic equations so a computer can understand and approximate the flow, right? Second, in computational fluid dynamics, we are studying we are particularly interested in a small portion of the universe, right? We have flow everywhere in the universe. Here in this room, I am surrounded by air mixed with other fluids, including uh, what, water in form of gas, hydrogen, nitrogen, which are all mixed up in form of air. Besides other fluids, there are fluids inside my body right now, such as blood and non-Newtonian fluid. So fluids are everywhere, essentially. So one of the things we must do when we are studying, we are interested in solving a problem, a physical problem or engineering design problem, we must separate a small portion of the universe, right? And study only this portion. Let's say you are a civil engineering who is designing dam, right? Or spillway or another hydraulic structure. And you're particularly interested in the pressure fluctuations at the bottom of a spillway dam due to the high stresses caused on the concrete, right? For just an example. Or you are particularly interested in studying the boundary layer caused by the airflow on our airfoil and the transition to turbulence in this airflow at the trailing edge of an airfoil, right? So you don't have to, of course. It can sound a little bit silly, but it's important to say that you don't have to simulate the whole universe in order to understand what is happening in your airfoil, in the boundary layer of your airfoil, or in the spillway of your dam, right? So we're gonna isolate this particular part of the universe that you are interested in and simulate flow only, and solve the governing the conservation equations only in this part of the universe, right? So this is what we call in CFD and numerical method, numerical simulation in general, domain, numerical domain. It's your domain of study, the domain in which we are solving the equations, right? So of course this domain must contain the essential parts and must be big enough in order to we describe correctly what is going on there. So we must assure that this domain doesn't gets interference from its borders, right? Because as we are isolating this part of the universe to study, it can be called a system, as an isolated system of the universe. The borders of the system must represent its borders with the rest of the universe. So we have to determine, uh, we have to be most, let's say, uh, we have to assure that it has a high fidelity, physical fidelity to what's going on right there, right? So as we define this domain, we define that it has borders. And these borders is where we are going to define our famous boundary conditions. That's where they came from. Our boundary conditions will describe the interaction of our domain of study of our physical phenomena to the rest of the universe. Let's say that this rectangle here, I don't know if it's exactly a rectangle, but let's say that this rectangle here is our domain of study. Here we'll study the airflow on this rectangle, and on its borders we must define the boundary conditions, or how will the conservation equations behave at the boundary conditions. So we have defined our domain, we have defined the algebraic, the numerical method to solve the conservation equations. And now we have to model our fluid. The conservation equations itself, they are not sufficient to describe fluid flow. We have to model the material, right, the substance which we are modeling. Air has its properties, water has other properties. We can have a multi-phase flow where we have air mixing with water, water mixing with oil, and many other types of fluids. We have Newtonian fluids, non-Newtonian fluids. We have compressive flow, we have compressive flow, we have laminar flow, transitional flow, turbulent flow. So these are many things that we have to keep in mind while doing a CFD simulation, a fluid simulation, right? So CFD is not a simple topic. Indeed, it's not. If we are simulating a turbulent flow, we have to couple additional equations, conservation equations. There are many models that we can choose to turbulent flow. We have to choose the most reliable and most consistent model for the kind of flow we are simulating. Right. So this was, in this video I intended to do a quick introduction to what is CFD and what we are what to expect, what we must look for when doing a CFD simulation. And I try to highlight the most important topics. So see you next time. Don't forget to like, to subscribe, and comment. And let me know in the comments what are your major interests in CFD, in computational fluid uh, dynamics, and which topics would you like me to talk about, in considering that it will be a basic introduction to numerical methods, to fluid modeling, and so on, right? So thank you for watching. Bye, and see you next time.